Hey guys, so we're doing this week in two parts because we have two quizzes, and I will be answering your questions while going over these quizzes. Alright, the ones that you've submitted for Muddy's points. So the first quiz we had was a conservation of momentum quiz, but it was just given to us as an explosion. Okay, so if you're not familiar with the problem, I put the problem in the description for this video. Alright, so go ahead and take a few seconds to read through that. So what we have is a mass. We don't know its mass. We know it's twice as big as the mass of the two parts it blows up into. Okay, so I called it 2m. It comes in at some unknown angle and at some unknown velocity. We're told that it blows up into two pieces, one piece with half of the mass going in the x direction with twice its velocity, and the other piece going at another unknown direction. Okay, so I use the label theta for the unknown direction for the initial mass, and phi for the unknown direction of the final mass. So the question is, what is the initial direction, which is theta on my diagram? Now your answers will depend on what diagram you draw, but the diagram you draw has to be consistent with the setup of the problem. Okay, so the law or definition. Well, we know that on the system, so on this mass, during the explosion, when it blows up into two pieces, the net force is 0. And we derived in class that we can rewrite the total force as the derivative of the total momentum with respect to time. I write this as a capital P, and I'll put a subscript syst for system. And we derived in class that we can write the total force on a system as the derivative of the total momentum with respect to time. So if those are equal, then this must also be equal to 0, which says that the total momentum in the x direction is a constant, and the total momentum in the y direction is also a constant, right? That's what it means for this time derivative to be 0. It's a constant vector over time, so its components must remain constant over time. So what we're going to do is calculate the components of the total momentum of the system just before the collision and just after the collision. Before, after, and we'll have a total momentum in the x and a total momentum in the y. So before, looking up here, we have this mass of 2m moving v in the direction of theta. Remember that the total momentum is just the sum of the individual momentums of each particle, where each particle has a momentum of m times v. The I subscript means for the ith particle. So before, we have one particle before the explosion. It has a mass of 2m and a velocity of v, and we need the x component. So it's 2mv cosine theta. And now because the total momentum has an x component that's constant over time, we then find the constant after, the total momentum after the collision in the x direction. Okay? So we sum up the momentum's x component for each mass here. So for this mass up here, the x component of momentum is m times 2v times cosine theta. Times cosine of phi. So I'm going to write the 2 in front, so it says 2mv cosine phi, just for reasons that I usually like to put the number in front of the letters. Now we sum up the x component of this momentum, which is m times 2v, all in the x direction. So I'm going to write the 2 in front again, and that's the total momentum in the x direction before the collision is equal to the total momentum in the x direction after the collision. Now we do the same for the y direction. 2mv sine of theta is equal to 2mv sine phi, and then nothing from this particle here. go ahead and verify that that's true for this picture, real briefly. Okay. So now that I have those two equations, I need to solve for theta. Well, right off the bat, we can divide both sides of each equation, this equation and this, by 2mv. And we're left with cosine theta. So divide both equations by 2mv. And for the x equation, we have cosine of theta equals cosine of phi plus 1. For the y equation, we get sine of theta. It's the sine of phi. Now let's call this equation 1 and this equation 2. And since we want to solve for theta, alright, you can see that we have two unknowns here, and trig functions always make things a little interesting to solve for, right? Well, if we use the identity that the cosine squared of theta plus the sine squared of theta, where theta can be anything, is equal to 1. Okay? So to use this, what we want to do is we want to square this first equation and then add it to the second equation squared, right? And the reason why that works is, let's say for example we have two equations. A is equal to B and C is equal to D. What's a valid equation that's consistent with that? Well, if I square A and I add it to C squared, that should also be equal to B squared plus D squared. Right? Go ahead and verify for a second that that indeed does make sense. And so we're going to use that same logic over here. Now before I do that, I'm going to do something sort of not obvious here, and I'm going to subtract 1 to both sides on this equation. So I get minus 1 here. Okay. Now the reason I did that is because when I go ahead and square the left-hand side here, I'll get cosine of theta minus 1, quantity squared. If I would have left that as just cosine theta, when I went to add the first equation to the second equation, it would have totally eliminated theta from the problem. You can go ahead and verify that subtracting 1 here is the right thing to do after seeing this next step. Okay. So we're going to take 1 squared and we're going to add it to 2 squared. Right? So we square the left-hand sides and add them together. Cosine of theta minus 1 squared plus sine of squared of theta is equal to cosine squared of phi plus sine squared of phi. And now I can use this identity twice. Once here, and once over here once I expand this. So I'm going to expand this term first. Expand. So go ahead and verify that when you expand that term, you get cosine squared of theta minus 2 cosine theta times 1 plus 1 squared, which is just 1. Okay, now I write the rest. This is going to be equal to 1. This plus this is equal to 1. So I'm left with 1 minus 2 cosine theta plus 1 is equal to, so this first one is just from taking cosine squared of theta plus sine squared of theta, and this second one is just from up here. Okay. And that's equal to 1 from this identity. Okay? And now we just solve for theta. You should get, subtract 1 to both sides, subtract another 1, and divide by 2. You get the cosine of theta is equal to 1/2. And go ahead and verify that theta then must be equal to pi divided by 3, or 60 degrees. Okay, I hope that was helpful. Now, you'll find that in a lot of these conservation of momentum problems, you'll also have to include some sort of energy conservation equation. And in order to do that, what you really need is some information about, for example, how much energy is lost in the collision, or maybe the internal energy, okay, in a nuclear reaction, okay. So unless we're given that information, it's hard to write down an equation without introducing a new unknown. If we were told it was, if we were doing a collision problem, we were told it was an elastic collision, elastic, that means the kinetic energy is conserved right before the collision and right after the collision. Okay, right. So energy conservation will also come into these momentum problems whenever information is given. Okay, that's it.